Albert Einstein's theory of general relativity, which has guided our comprehension of space, time, and gravity for over a century, is now at the center of a revolutionary debate. What if Einstein's equations are incomplete, or even flawed? What does this mean for our understanding of the universe itself, and what new paradigms could emerge from this seismic shift in thought? To truly appreciate the significance of this study, we first need to examine the towering legacy of Einstein's contributions, particularly his groundbreaking theory of general relativity. Einstein's legacy: the triumph of general relativity. In 1915, Albert Einstein published his theory of general relativity, a work that completely transformed how we understand the fundamental forces of the universe. General relativity is, at its core, the idea that gravity isn't just a force pulling objects together but a warping of space and time itself. Massive objects like planets and stars cause space-time to curve, and this curvature is what we perceive as gravity. It replaced Newton's centuries-old concept of gravity as an invisible force with a far more elegant and powerful model. For over 100 years, this theory has stood the test of time. It has accurately predicted everything from the bending of light around the sun during solar eclipses to the detection of gravitational waves, ripples in spacetime caused by massive cosmic events. Time and again, general relativity has been confirmed through experiment and observation, providing humanity with an unprecedented understanding of the cosmos. But as robust as general relativity is, it has always faced significant challenges. For one, it cannot reconcile with quantum mechanics, the theory that governs the behavior of particles on the smallest scales. While general relativity explains the large-scale structure of the universe, quantum mechanics operates in an entirely different realm, where particles exist in multiple states simultaneously, and where uncertainty and probability are at the forefront. For decades, physicists have dreamed of a unified theory of everything, one that could combine both the grand theory of general relativity and the peculiar world of quantum mechanics. Yet, despite countless attempts, this elusive theory has remained just beyond our reach. And now, with this new study, we may be getting closer to realizing why. A new study, a new paradigm. This groundbreaking research, conducted by a global team of astrophysicists, suggests that the universe is behaving in ways that Einstein's equations cannot fully explain. The study, which uses data gathered from cutting-edge telescopes and satellites, points to inconsistencies in the way galaxies rotate, the distribution of dark matter, and the accelerating expansion of the universe, phenomena that defy the predictions of general relativity. One of the most startling discoveries in the study is the apparent breakdown of the behavior of dark energy, the mysterious force driving the universe's accelerated expansion. In Einstein's model, gravity should slow down the expansion of the universe over time. However, observations show the opposite: the universe is expanding faster than ever before. To account for this, scientists introduced the concept of dark energy, a force that constitutes about 68% of the universe's energy content. But here's the kicker: no one knows what dark energy actually is. It doesn't interact with matter or light and can only be inferred from its gravitational effects. Einstein initially considered dark energy when he introduced the cosmological constant, a term he added to his equations to describe a static universe. He later discarded it, but the idea of a constant force lurking in the fabric of the cosmos still haunts our understanding. However, this new study suggests that the explanation offered by the cosmological constant doesn't quite fit the observations. Instead, the data points to something much more dynamic, a force or phenomenon that is fundamentally different from what Einstein had envisioned. This could suggest that our entire theory of gravity needs a serious update, one that goes beyond general relativity. Dark matter, the invisible glue of the cosmos. Just as dark energy poses a challenge to general relativity, dark matter remains another massive enigma. This invisible substance is believed to make up about 27% of the universe and is thought to be responsible for providing the gravitational glue that holds galaxies together. Without it, galaxies would spin apart, their stars and gas flying off into space, unable to hold on to one another. But despite decades of searching, no one has ever directly detected a single particle of dark matter. Now, the new study shows that the distribution of dark matter in some regions of the universe doesn't match the predictions of Einstein's equations. This is another glaring sign that general relativity may need to be rethought. Perhaps the way we understand dark matter is incomplete, or perhaps gravity itself behaves differently on larger, cosmic scales. Either way, this is a major clue that something is amiss in our understanding of the fundamental forces of nature. The Hubble constant dilemma, a cosmic crisis. Then there's the long-standing mystery surrounding the Hubble constant, the rate at which the universe is expanding. For decades, two different methods of measuring this constant have yielded different results. Observations of the early universe, such as the cosmic microwave background, the afterglow of the Big Bang, suggest one value for the Hubble constant, while measurements taken from the nearby universe, such as those from supernovae and Cepheid variable stars, suggest a different value. This discrepancy, which has only grown more pronounced as measurement tools have become more precise, hints at a fundamental flaw in our cosmological models. This new study suggests that the discrepancy between these two measurements cannot be explained by the current framework of general relativity. Rather, it points to the need for a new theory of gravity, one that can account for both the accelerating expansion of the universe, and the mysterious forces of dark matter and dark energy in ways that Einstein's equations cannot. The future of physics, a new theory of gravity. Does this mean Einstein was wrong? Well, not exactly. His theory of general relativity has proven incredibly accurate in many situations, just as Newton's laws did before them. But like Newtonian mechanics, which was eventually superseded by general relativity, it's possible that Einstein's theory could be replaced by a more comprehensive model that better accounts for the mysteries of the cosmos. So, what might this new theory of gravity look like? Several ideas are already on the table. Modified gravity. This hypothesis suggests that the laws of gravity might change under certain conditions or at specific scales, potentially offering a more accurate description of how gravity works in the vast reaches of the cosmos. Emergent gravity. This idea proposes that gravity may not be a fundamental force at all, but an emergent phenomenon that arises from deeper quantum interactions. Extra dimensions or new particles. These concepts involve entirely new forms of energy or additional dimensions of spacetime that we have yet to discover. These ideas may seem radical, but they are driven by one common goal: to reconcile the gaps in our current understanding and provide a more unified theory of the universe. Time, reality, and the multiverse, unveiling the deepest mysteries of existence. If general relativity is incomplete, the implications stretch far beyond just gravity. We may need to revisit some of our most fundamental assumptions about the universe, such as the very nature of time itself. In Einstein's universe, time is not a fixed, unchanging constant. It is relative. It speeds up or slows down depending on how fast you're moving or how close you are to a massive object. But what if time, as we experience it, is merely an illusion? What if the flow of time, the past, present, and future, are constructs created by the human brain to make sense of an incomprehensibly vast and complex universe? This possibility opens up a whole new realm of philosophical and scientific questions. If time is not a continuous, linear flow but an emergent property of the universe, then the very concept of causality, where one event leads to another, may need to be rethought. Could we manipulate time? What might this mean for the very essence of human existence, free will, and morality? As we delve deeper into the nature of time, we also explore the tantalizing possibility that the universe is part of a vast multiverse, an infinite sea of parallel universes, each governed by its own set of physical laws. The discovery of dark energy and anomalies in the Hubble constant suggest that our universe may not be an isolated system but part of a much larger framework. If the multiverse exists, it raises profound questions not just about physics, but about the meaning of life itself. Could there be other versions of ourselves in parallel universes, living out alternate lives? And if each universe has its own set of laws, how do we reconcile the fine-tuning of our own universe, one so exquisitely calibrated to support life, with the possibility of other universes where such conditions may not exist? A new era in physics and humanity's quest for knowledge. This new research may challenge the very foundations of what we know, but it is also a testament to the true spirit of science. The willingness to question established ideas, to search for answers in uncharted territory, and to embrace the unknown is what drives progress. As we enter this new era of physics, we must remain open to fresh perspectives and ideas, prepared to discard old paradigms when the evidence demands it. It's a journey that has just begun, one that will redefine our place in the cosmos, our understanding of existence, and perhaps even the nature of reality itself. What lies ahead is uncertain, but the road ahead is one worth traveling,